let's get started. There's going to be some interesting stuff today. So we're going to finish up regular old Lewis models today and go into molecular shapes and valence bond theory and molecular orbital theory stuff today, okay? This stuff is really, really valuable to you because your first few chapters in organic chemistry are going to be about the molecular shapes, valence bond theory, and the molecular orbital theory. In fact, a lot of the the material in here is from an organic textbook, not from the Gen Chem textbook, because they actually explain it in organic chemistry better than they do in Gen Chem, okay? So let's finish up Lewis structures real quick. There's nothing too difficult going on right now, right? So if you remember when we were talking about Lewis structures before, right? I went through, and if you haven't seen it, you can look at it in the video, how to make a Lewis structure. The point of the Lewis structure is to have your central atom have a full octet, right? And sometimes, like we were talking about last time, if you have a molecule that doesn't have a full octet, you have to move bonds around to make it so it will have a full octet. Well, let's take a look at this molecule here. This is the molecule ozone right here, right? This is molecule ozone. The problem is that when you add all of ozone's electrons together, right, there's not enough electrons there, or wait a second, it's either not enough or too few electrons to actually give all of them a full octet, all the oxygens a full octet, right? And so what happens is that instead of having one Lewis structure, right, whereas everything you saw last time had one Lewis structure, this is going to have, ozone will have two Lewis structures, right, where the bond between the oxygens are going back and forth. Oh, I forgot to change it to drawing. Let me change it to drawing real quick. There we go. So notice here, right, this oxygen has a full octet, right? This oxygen here has actually a full octet as well, but this one does not have, this one also has a full octet too, but the problem is that one of them over here, wait, I'm sorry, I said that wrong. Oh, sorry, yeah, this has a minus charge, okay? Because it actually has an extra electron right there, right? So this one right here actually is a minus charge, okay? So what happens is that this extra pair of electrons, remember, because oxygen usually looks like this. I was going to draw on the board, but that's okay. Oxygen usually looks like this, right? And then this is, whatever else, okay? But for some reason, this oxygen here only has one bond and 3 lone pairs, right? It's supposed to have 2 lone pairs, right? So there's an extra electron there. That's why it's got a minus charge. And so when you have a structure like this, where you have an extra electron on this oxygen, and then the other 2 are already satisfied by octet, you've got to do this thing called resonance, okay? And resonance means that the electrons flow back and forth between each other, right? Between each atom. And that's called resonance. So what happens is that, let me erase this mark real quick. What happens is that there's a negative charge here. When you do this one's formal charge, when you do that oxygen's formal charge right there, there's a negative on it, right? -1. And what can happen is that this negative charge can come down and form a bond right there, a double bond right there, right? But the problem is that when you do that, you get this thing here, like that, right? And now this oxygen right here has more than 8 electrons, bigger than an octet, correct? Right? And so, is oxygen one of those ones that can have a bigger octet? No, it's not. It's not like phosphorus, right? So what happens is that the bond that used to be here will go to that oxygen, right? And then the next structure is this over here, and now this oxygen is the one that has negative charge, okay? Instead of the one that was on the right. So you can see that these electrons are bouncing back and forth between the oxygens. And the reason why we know that this is true is because we can do a thing here where we look at, we saw this last time too, where we saw the polarity, right, of the atoms in the Lewis structure, okay? And in the polarities, it actually shows that most of electron density, the negative stuff, is on the ends, right? It's on the side oxygens, not the one in the center, right? But how is that possible when you only have something like this, where the negative charge is only on one side, right? And then over here, it's only on one side. Well, the only way that you can explain that is that these electrons are here, this negative charge electrons that are bouncing back and forth, making a double bond here, turning that into a single bond, right? Giving that a negative charge, and then going back again, right? And going back and forth between the two. And so we call that a resonance hybrid, okay? That's called a resonance hybrid, because this negative charge can go back down, form that bond again, okay? And then now this bond right here breaks from the double bond, giving that electron back to the oxygen. So it looks exactly like it did on the other side, right? So chemistry and chemists believe, right, and we know pretty well through instrumentation, that the actual Lewis structure is actually something in between, okay? It's actually something in between having the negatively charged oxygen over here and the negatively charged oxygen over here. It's actually something in between. But we want to show how we get from one place to the next. So the actual Lewis structure of that molecule looks more like this, with these dots right here. That's the actual Lewis structure of ozone, right? Because the dots show that the double bond is actually kind of temporary, and it's actually something in between, okay? It's something in between. Now, when you go into organic chemistry, organic 2, which will be your next class, right? Or organic 1, rather. Don't jump into organic 2. That's just crazy. When you go to the next class, which is organic 1, like I said, half your time you're going to be doing resonance, okay? So you're going to have to deal with all kinds of different molecules, right? All right, so everything I just said out loud is actually said in these words, okay? So just so you know. All right, so let's take a look here at some more resonance, okay? Another compound that has a lot of resonance is a compound called benzene, C6H6, right? And this is benzene right here. Notice that in this structure, every single molecule has an octet, right? Well, except for the hydrogen, because it has a full decet, I guess it would be, since it's only 2 electrons for a hydrogen. But this carbon here has 4 bonds, 4 bonds, 4 bonds, 4 bonds, 4 bonds, 4 bonds. But it does undergo resonance, right? Just like the ozone does. This bond can come down here. This bond can come over here. This bond can come over here, like that, okay? And then you get this structure now, right? So really, in Gen Chem, they lied to you when they said the Lewis structures are the way that molecules look. It's not true, actually. It's the most simplified way you can do it, right? What they really look like is actually a combination between the two of these, which is what we call the resonance hybrid, right? And so in organic chemistry, we actually make it look like this now. A benzene has a circle around it, right? And that circle is kind of like those dots that I put on the oxygen that indicate that these electrons are flowing around the orbitals, the p orbitals, right, in this circle, in this ring, okay? So there's a technical term for electrons that can do resonance, right? That technical term is they are delocalized, okay? Electrons that can do resonance, or electrons that can be shared by multiple atoms, they're called delocalized, right? They're called delocalized. And then there are electrons that don't get shared, and those are called localized electrons. You'll never see a localized electron do resonance, okay? They're only usually localized electrons are usually the electrons that only are shared between one atom, like a lone pair, right? Or they're shared just between 2 atoms, making a single bond, okay? So here, then, your delocalized electrons are going to be the ones here in the double bond, right? Because those are actually p orbitals. We'll talk more about that in a minute, okay? And then the bonds that are here between the hydrogen and the carbon they're known as sigma bonds or s orbitals, okay? That's where your localized electrons are, because you're not going to see those bonds going anywhere from the hydrogen, okay? That makes sense? Excuse me. All right. So let's talk about the exceptions to the octet rule, right? We kind of dabbled in it a little bit last time because we were talking about phosphorus, right? We had phosphorus here that, remember, what's the rule about phosphorus? Anybody remember? Say again? Yes, but what was the other rule about phosphorus? It loves oxygen, right? Remember that. That's really important. Phosphorus loves oxygen. It will break bonds to be with oxygen, okay? But we already said last time, too, that it also can break the octet rule, right? It can do something like that, okay? The reason why is because once you get from row 3 below, right, you have more electrons you can play with, okay? You have more electrons you can play with. So these are the exceptions to the octet rule. Ions are molecules with an odd number of electrons, right? They are an exception to the octet rule. Makes sense, because if you have an odd number of electrons, how are you going to get to 8? Right? There are some that will do that. I'll show you one in a second. I mean, there's just no way getting around it. They're unstable, but they do exist. Ions are molecules with less than an octet. What's a good example of something with less than 8 electrons total? Boron, right? Boron can only form 3 bonds. Remember? 3, 4, 5, 6, right? So, sorry, let me say that again. 3 bonds, right? 4 bonds, 3 bonds again, but more electrons, right? 2 bonds, still more electrons. 1 bond, still more electrons. So literally, boron here has 3 bonds to form, right? And only 3 valence electrons to do it with, okay? And then the last one is that ions with more than 8 valence electrons are an expanded octet, okay? Which is phosphorus, things like phosphorus. Really, anything that's beyond phosphorus can do that, right? Not anything over here that only has like 1 bond, right? But anything that's 3 and below can do that kind of thing. Okay, so let's go through each of these rules one at a time, just to make sure you got these rules, okay? That way, when you get them on a test or something, which our first test isn't for like 2 weeks, so thank God for that, right? So, okay, the clock's right today. Okay, just making sure. Yesterday or something, or last time I said it was like 9 o'clock. I'm like, really? I've only been here for like an hour? And so here is an example of an odd number of electrons, okay? Odd number of electrons. So we have here an oxygen, right? It's got a full octet, right? But nitrogen doesn't have a full octet, right? It's missing an electron, okay? Which makes sense because nitrogen only has 5 electrons, right? So you do some resonance with that, and then you can get this molecule over here, right? You can get that molecule over there. But notice that it doesn't have a full octet on both because it doesn't have enough electrons. It's an odd number, right? It's an odd number of electrons, so it doesn't have an octet on both. Now, if you're wondering what this molecule is, this is nitrous oxide, or nitric oxide, either nitric or nitrous. I can't remember. I always get the two confused, right? And it's actually the molecule that gets produced when people take Viagra, right? It's a thing that causes erections. And the reason why it does is because when you take Viagra, this gets produced, right? And this molecule, nitric oxide, is actually, what it does is that it's a vasodilator, right? It opens up your blood vessels, right? No matter what gender you are, it opens up your blood vessels, right? So this is actually the thing. The molecule that actually is in Viagra is called like Synfindel or something like that. SY, I can't remember these. It's something SY, something DEIL, or something like that. But when you take it, it makes that stuff. And that's why people take Viagra. I thought so too. Oh, look at this. Fewer than 8 electrons. And the example I gave you before we even got to this page, this before I even got to this slide, was boron, right? There's boron right there. How many valence electrons does it have? Right? 3, correct? It only has 3 bonds to make right here, right? It can't do anything without. How does it get to 8? Right? How does it get to 8? It can do some resonance, right, and get to 8 when it bonds, double bonds with fluorine, right? But the problem with the double bonding with fluorine, though, is the fact that fluorine is more electronegative than boron is, right? And when you put a double bond on fluorine, it turns fluorine into a positive charge, and it turns boron into a negative charge, right? It makes sense because you're giving boron an extra electron that it didn't have before, right? 1, 2, 3, right? Well, now it has 1, 2, 3, 4, right? So it gives boron a negative charge. But you took that electron from somewhere. Where'd you take it from? Fluorine, right? Or fluoride, okay? And it gives fluoride a positive charge. What's wrong with that? We talked about this last time. When you're drawing Lewis structures, right? What's the rule about charges, about formal charges? Yes, that's the first rule. What's the second rule? Negative charge. Exactly. The more electronegative ion gets the negative charge. So, which is more electronegative here? It's fluorine. It's definitely not boron. Boron's in the middle of the periodic table, right? It's barely electronegative at all, right? So really this negative charge needs to stay on what? Fluorine. And that's why it says that all of these resonance structures, though do exist, are very fleeting. They're very fleeting. They don't exist for very long. Because the most stable version is the one where boron has 3 bonds and is a positive, is a neutral charge, right? And fluorine is the one with the neutral charge but has the most electrons. That make sense? Yep. Make sure you know that will be tested. All right, more than 8 electrons. We talked about this already before. Here's phosphorus, right? And the picture that I drew for you last week and the one I drew just now is this picture right here, right? Where it was a double bond to phosphorus with an oxygen and then single bonds to oxygen all the way around, right? And notice the thing I want you to really know here, or notice here, is that these oxygens that have single bonds, what are their charges? They're negative, right? Is that good or bad? It's actually good because oxygen is what? More electronegative than phosphorus is because it's higher on the periodic table. So it's okay that oxygen has a negative charge, right? And so you could actually go through like I was showing you before, like not yesterday, but Wednesday, right? Where you can make these electrons come down, and then this double bond comes up here, and then you have the double bond now on the oxygen at the top, and the extra electron over here on that oxygen on the left. You can go all the way around in a circle. That's all called resonance, right? And the reason why it has to be done that way with the oxygen is because, again, oxygen has how many bonding pairs that it needs to have? 2, right? It needs to have 2 electrons that can bond with, because it has 2 bonding pairs, or 2 bonding electrons. But for fluorine here, fluorine has a single bond, right? Single bonding electron. So it can just literally put 5 around it, and it's happy with no double bonds. Does that make sense? Right? You don't have to do any resonance with fluorine here, right? Fluorine is more electronegative than phosphorus is. Okay? So all the electrons are going to be on what? Fluorine. Okay? And then phosphorus will be in the center. It just needs 5 bonds to be happy, right? Because it's got 5 valence electrons just hanging out there just like nitrogen does. The difference between nitrogen and phosphorus, though, is what? 1 pair of electrons from nitrogen is already a lone pair, right? So that's why it only has 3 bonding electrons. But phosphorus doesn't have any lone pairs that are available at the moment, right? They're all bonding electrons, right? And there's 5 of them because they're in the same group as nitrogen, and that's why phosphorus has 5 bonds, right? Make sense? Remember, all of them have the same properties when they're in the same group, okay? when they're in the same group. All right, your first question for today. Go ahead and scan it. Make sure you're on the Texas Wesleyan Wi-Fi so you don't get asked to log in multiple times a day. Which of the following is not an exception to the octet rule? I'm starting off easy here. Starting off easy for you. Oh, I forgot to log onto the computer so I could see how people are answering. Oh crap. Oh crap. Everything good? Everybody logging in? All right, I log into this thing every Wednesday and Monday. Why are you getting ready? Like, shouldn't you already be ready? You guys notice I'm a little more professional today. I've got a collar again. So, still wearing, scrub pants, but at least I'm wearing a collar. Really? I have to log in again? What the heck? And of course, I have to give you a code. Maybe there's students that are hacking into my account trying to change their grades, and that's why I have to do this. All right. Okay. We are doing the octet question. There are 12 people in here, right? Are there 12 people in here? You're there? Okay. I'm like having trouble counting for some reason. Okay. Let's see what everybody put. All right. Okay, so the answer to this one actually is none of the above because they are all exceptions to the octet rule. All of them are. Right? So that's an easy question. Make sure you know that answer so you can answer it correctly on the test. That's a really easy question considering I just talked about it. Yeah, it says what is not. So all of these are actually octet rule exceptions, right? You should do that on the exam. Oh, yeah. See, I know that's a problem sometimes, and that's why I capitalize the not for you. So be careful with that, okay? Be careful with that. All right. So let's take a look at this real quick here. We have some bond enthalpies. Here's another vocabulary word you should know, okay? Another vocabulary word. Bond enthalpies, right, are the energy that is required to break a bond, okay? They're the energy required to break a bond, right? So to break a bond, you actually have to do what to the bond? You have to put energy into it, right? You've got to put energy into it. Is that an endothermic process or an exothermic process? Exactly. It's an endothermic process, right? Say again? What's stronger? Endothermic stronger bond?
Like exothermic is like the weaker.
No. Exothermic is when you release energy. Endothermic is when you put in energy, right? There's not really weaker or stronger, right? So, I lost my train of thought. Okay, so we're breaking bonds, and bond enthalpies are the amount of energy required to break a bond. And you've already said this before, it is an endothermic process. Why? Because you've got to put energy into breaking bonds, right? You've got to put energy into breaking bonds. And so enthalpies are always positive because every time you have an endothermic process, right, the number is always going to be positive. A positive number indicates that energy is going into the system, right? Because that system is gaining energy, it's getting positive in energy, right? What's the sign of it's losing energy? It's negative, right? If it releases energy, then it's losing energy, right? Then it's negative, and that's the exothermic process. Does that make sense? Is your battery dying?
Oh, well, it dies like really good with that.
Yeah, mine does that too. I said mine does that too. My laptop's from like 2012. I'm supposed to get another one soon, but they haven't sent it yet. Anyway, right? So these are all the energies required in grams per joule, kilojoules per mole, right? Required to break a bond, okay? So one of the things I did want you to notice about this chart, I'm not going to make you memorize the chart or anything like that, but is this right here, carbon-carbon bonds. It takes about 348 kilojoules per mole, okay, to break a carbon-carbon bond. That's interesting, and the reason why it's interesting is because if you were to take kilojoules per mole and convert it over to nanometers, it's around 200 to 300 nanometers, which is the same energy as UV light, right? It's the same energy as UV light. What does UV light do to you? Yes, it gives you cancer. Specifically, it gives you skin cancer, right? What is your DNA made of? Carbon-carbon bonds, right? So literally, UV light is the perfect amount of energy to go in and break the carbon-carbon bonds of your DNA, right? And that's why you get skin cancer. Not you personally, but, generally, right? So that's the interesting thing about that. These are all the energies that are required for bond breaking of these types of molecules here. And the thing that makes us live, our DNA, is composed of carbon-carbon bonds, and it's the exact amount of energy that the sun gives off in UV radiation, right? Yeah, absolutely. It's the same light we use in the crime lab called an ALS, an ultraviolet light source, and it actually shows the one I used to use actually had at 400 nanometers, not 200 or 300. So it's a bright blue light, and it will show you where parts of your skin cells have died from because it doesn't come back the same color anymore. It doesn't reflect off the same color anymore. So crazy stuff. You can also use that same light to find blood, sperm, all kinds of stuff, right? Yes. Fingernails, toenails, like clippings, all kinds of stuff. So that's really the only thing I want to talk to you about that. That's the important thing about bond energies, right? Okay, so we talked about this on one Monday already, but remember that bond enthalpy and bond length, right? As the number of bonds increases between two atoms, the bond length decreases. Remember I said that, right? The shortest is going to be the triple bond, right? The middle one is going to be the double bond, and the longest bond is going to be the what? Single bond, exactly. 10 points to Griffin. Damn it. Hufflepuff. Huh? Yeah. I said this last time already, but I'll say it again. The more bonds you have, the shorter the distance is between the two atoms that are connecting, okay? So 3 bonds is the shortest, a double bond is in the middle, and then single bond is the longest. And we're going to see why in a second, right? So here is a little graph that shows you the length between nitrogen and nitrogen, like nitrogen gas, right? And over here, we have nitrogen with a single bond, and its length is over here by like 1.5 angstroms. But then when you get nitrogen with 2 bonds, right, double bond, it's 1.2, between 1.2 and 1.3 angstroms. But then with a triple bond, it's almost at 1 angstrom, okay? And we can find, a lot of people ask, how do you know this? It's because someone did an experiment and found it out, right? Had data. And that's where we get this from, okay? We don't make this stuff, well, we make up some stuff, but we didn't make that up, okay? All right. Everybody ready? I don't want to move on if this is confusing. Oh, I think someone knows what I'm about to do. They're predicting how many questions I have in there now, aren't you? All right. Bond enthalpies are positive and endothermic, positive and exothermic, negative and endothermic, negative and exothermic, or none of the above. If it is the last thing I do, I will teach you all chemistry. Every one of you. Okay. Okay, only 9 responses so far. Are you having problems again? Hannah, are you having problems again?
Okay.
You sure?
I got it.
Okay. I mean, you can do the paper thing like you did last time if you need to.
No, it's fine. I have to log in every time. I have to log in every time too.
Are you on the Wi-Fi?
Yeah.
Are you on the secure Wi-Fi or are you on the registered Wi-Fi?
I have no idea.
Yeah, you need to be on the secured Wi-Fi for it to work. You're not having to log in every time. It's okay. We wait for you. Yes, I have seen the show, Dexter. I do too. Don't tell me what happened though, because I haven't seen the last season, and I'm putting it off because I don't want to know because I heard it was really bad. Like it. Yeah, exactly. We only have 9. We need 3 more people. 11, good. 1 more person. That is really weird.
And I had to make a super difficult password. Even though my last password was the easiest password, they made me make a super difficult one with literally 25 letters long.
Holy mother. Congratulations! Everybody got the same answer, and everybody gets points. Good job. Oh yeah, I forgot. So part of the reason it's a good thing we're not going to have class on Monday because it'll give me a chance to finalize the rules of the House Cup and then put them on the blackboard so that you can see how many points each team gets at the end of the semester. And I'm also going to tally up everybody's points so you see your rankings at the end of every week. Okay. What happened? You say you're pretty sure you're winning the game? I'm not surprised. I'm not surprised that you're winning. Okay. Good job. Everybody at least understood what I said there about bond enthalpy. Good job. All right. See, and I didn't have any faith in you, I guess, because I had this one as one of the ones where you had to discuss it with your house. So, good job. You don't have to do that. Okay. This is really quick and easy. I just want you to be able to see the difference between having strong covalent bonds in this molecule like pentane right here, but then when you have a flask or a beaker of pentane, right, there's a whole bunch of pentane molecules inside, and they're being attracted to each other with what we call van der Waals interactions. We'll talk about that later. You don't have to write that down, but they're not attracted to each other with a covalent bond. They're really just kind of associating with each other because of these interactions that make them electrostatically attracted to each other, not as a covalent bond though. So they're not sharing electrons. So what happens is that if you heat up the flask or the beaker of pentane, right, you put in enough energy to break these interactions right here, and it doesn't take much. It doesn't take much, and it will evaporate. So when you have a liquid, right, for example, water is being held together in your flask, right, or in your cup. Water is being held together with hydrogen bonds, right? Not the O's and the H's, those atoms, but the H2O's with other H2O's, right? Okay? They're being held together with hydrogen bonds. Can anybody tell me how much energy it takes to break a hydrogen bond in water? No, not at all. Not much at all, actually, right? How do you boil water and it evaporates? It's 100 degrees Celsius. That's all the energy you need to break the hydrogen bonds that are in water, right? Let me draw it out for you. Yeah. So there's the water molecule, right? And literally the water molecule is doing the same thing as this pentane is, right? Except instead of it being called van der Waals interactions, it's called hydrogen bonding, or we call it H bonding. It's much weaker than covalent bonding, much weaker than ionic bonding, right? Well, collectively, we're talking about so that's complicated, right? It depends on the hydrogen bond number one, right? Because you don't have to just have hydrogen bonds with oxygen and hydrogen. You can have hydrogen bonds with any hydrogen and any electronegative atom, right? So it depends on the hydrogen bond number one, right? It depends on how much heat you put in there, and it also depends on how much it is in there. And you're right, water's hydrogen bonding is very strong. That's why you get surface tension of water. Grasshoppers can jump on top of water and they don't sink because they're on the top of water. Those hydrogen bonds are holding it really well, right? So, but there are other hydrogen bonds that don't do that. You put a grasshopper on that and they'll just pass right through, right? So it really depends, right? But you're right. They are strong, right? But you shoot in there some heat, like 100 degrees Celsius or 212 degrees Fahrenheit of heat, right? And that's all the energy you need, right? To break that hydrogen bond in half, and then the water evaporates, right? But to actually break the hydrogen off the oxygen takes way more energy than that. You actually have to run electricity through water to do that, right? And that's the basis of like hydrogen fuel tanks, like those cars that they were trying to make more energy efficient, and they put like hydrogen fuel tanks in there, and they put like there's these bubbles coming up and stuff. That's really that might have been a while back.
Wait, to knock the oxygen off the hydrogen or the hydrogen off the oxygen?
Well, okay, the first thing I was talking about was using 100 degrees to break the hydrogen bond between two water molecules. But to break the bond, the covalent bond between the oxygen and the hydrogen, it takes way more energy. You have to put electricity in there. The last thing I want to talk about as far as bonding goes, the type of bonds, is metallic bonds. This will probably be the last thing I ever say about metallic bonds because it's not really a big focus. That's why we don't even talk about the D block, because the D block is all metals, We don't even talk about it that much, okay? But the big thing about here is that metals have low ionization energy, so they lose electrons easily. You knew that already because sodium here can just, it's just so gracious, so generous, it will gladly give up its extra electron and give it to chlorine, right? And chlorine is so greedy, taking electrons from kittens, right? It'll take it, right? It turns out that all metals are that way, right? They'll lose electrons super easily just to get to their happy octet or their happy full outer shell, right? And so we have a whole bunch of metals together, right? They're all sharing their electrons with each other, right? And so now what you have is this thing called an electron sea, right? And it's an electron sea. The interesting thing is that this is how you come up with you mix two different metals together and you get alloys, right? For example, steel or bronze, right? Or what are some other alloys? It's the only thing I can think of right now. Anyway, you can change the property of the metal, make it stronger, make it more malleable, change its melting point by mixing them all together because these electrons are so in a sea that when they mix with each other, right, since they're not actually being transferred or sharing, like in the traditional sense, other metals can actually go in between and change the properties of between the atoms and change the properties of the metal themselves. And that's all I really want you to know about that. What happened? Huh? Oh, I thought you were. Oh, sure, you were asking me a question though. Oh, okay, sorry. So yes, just know that metallic bonds have this. It's a delocalization of electrons, and it's called an electron sea. That's all you need to know about that. Yeah. Yeah, go ahead. If you need to use Russian, you don't have to ask me. We're not in high school. If you need me to give you a hall pass or something, then maybe, but I'm just gonna scream out there, kids, go into the bathroom as your hall pass. Yeah, I actually posted new notes this morning. Oh, you did? Yeah. Okay. Oh, last night. I posted new notes last night. Okay, so let's keep on trucking here. Let's keep on trucking. So let's remember when we spent all that time talking about the repulsion between two electrons. the repulsion between two nuclei, and the attraction between one electron and one nuclei. Remember that? Yes, we spent a lot of time talking about that. So, and so this is actually the experimental example of that right here, right? We have two nuclei. We've got a hydrogen nuclei here. Which ones? Oh, these? Just so that they can be, they're coming together to make a bond, and so we have two nuclei here. We have a hydrogen atom here and a hydrogen atom there, right? And two hydrogen atoms can come together and make the hydrogen molecule, which is H2, and H2 is a gas, right? And so when we're talking about two nuclei coming together, like I said before, we've got that repulsion between two nuclei, we've got the repulsion between two electrons, but then we have the attraction between an electron and a nuclei. And so what happens is that when the two atoms are over here, so notice on this graph, we have intermolecular distance is on the x-axis, and we have energy that's on the right, the y-axis. And so the further the two atoms are from each other, the less they're interacting, right? Right? The attraction is minimal, right? The repulsions are minimal in all the cases. But then, as they get closer and closer to each other, right, the attraction between the electron and the nuclei, right, become so great that it overcomes the repulsion between the two nuclei and the two electrons, right? And that's when you get to this very bottom thing here, this little trough at negative 436 kilojoules per mole of the hydrogen molecule, because when they're this close from each other, 0.74 angstroms, they're at the perfect distance, right, where the attraction between the nuclei and the electron is stronger than the repulsion between the nuclei to each other and the electron to each other. Does that make sense? So the only way you're going to get a bond formed, right, is if the attraction between the nuclei and the electron is stronger than the repulsion between the two nuclei or the two electrons by themselves. Okay? But the funny thing is, look, as you get closer and closer and closer to zero, right? So the nuclei are getting so close to each other. There's a point where they get so close that the repulsion takes over, right? The repulsion takes over and the energy goes super high. And hydrogen gas doesn't like that, right? Yes, because what does it mean to get closer to zero on this graph? It means that those atoms are getting they're like literally like up against each other, right? The distance between them are up against each other, okay? And so hydrogen would be hydrogen gas much rather down here, right? It doesn't want to be all the way up there, where the energy is really high. So the point of this is that at some distance, two nuclei will not even notice each other, right? They won't even notice each other. But then as they come closer and closer to each other, they'll start noticing each other, right? And then when they get close enough, where their attractions overcome their repulsions, right? That's when they become a molecule. But if they get too close to each other, right, they won't become the molecule anymore. They just shoot up energy, and they're not happy anymore, or you won't have that molecule anymore, right? It depends on the molecule. Usually it just splits up, and usually breaking a bond does cause an explosion, yes. So, yes. But yes, hydrogen just likes to be right here in this little trough, okay? That's true of every covalent compound, okay? All right. So, this is where we really dive deep, right? We dive really deep into orbitals, okay? We dive really deep into orbitals here, okay? So, remember when we were doing electron configurations, and we were talking about the s orbitals, the s block, and then the d block, the p block, and then the d block in the middle, and the f block over here at the bottom, right? Those aren't labeled that just because, we thought that was cool. They're actually the name of orbitals, okay? So here, right here, we have an s orbital, okay? 2 electrons can fit in that s orbital, this ball right here. The center is the atom itself, right? And then this ball has an s orbital, okay? There's 2 electrons. Just so you know, you can only fit 2 electrons per orbital, no matter what orbital it is. It only fits 2 electrons. So here we have 3 p orbitals, okay? Yes. Yes. it doesn't even matter. Any orbitals can only fit 2 electrons at a time, okay? Any orbitals, whether it's a p orbital, d orbital, s orbital, it's always 2 electrons at a time, okay? But the thing is, these are 3 p orbitals that are all of the same energy. We have the py orbital, we have the px orbital, and the pz orbital. Why are there 3 p orbitals? Yes, but also, what else? How many electrons are in the p block? 6 electrons. You can only have 2 electrons per orbital, and that's why there's 3 p orbitals. Right? Does that make sense? I don't even know what these are so complicated. We don't even want to go there. There's 6 electrons in the p block, yes. Yes, in the p block. And the reason why there are 3 p orbitals, because, yes, exactly, there's 2 per orbital, right? And it's 3 times 2 is 6. Okay? So these are all called atomic orbitals. And what these signify is it's about 9. And the shape of that graph, or that 3D model inside of that graph, is these shapes, right? And that's why we think that this is what an atomic orbital looks like, and it's like 95%, where the electrons are present. So let's talk about the phases of an atomic orbital real quick. You saw before that the s orbital was just one blue thing, right? But then you saw that the 3 p orbitals had red and blue, okay? Those are the different phases of the p orbitals, okay? They're the different phases of the p orbitals. And a phase is actually denoted with this Greek letter psi, okay? The Greek letter psi. And it's really simple. They can either be in the positive phase or the negative phase, right? They can either be in the positive phase or the negative phase, right? And so when you split the wave in half, right, and the reason why we have this looking like a wave is because electrons, right, can actually act as a particle or a wave. So when you describe an electron as a wave, okay, waves go like this, obviously, and you can split the wave in half, right? And the top part of the wave has a phase of positive, and the bottom part of the wave has a phase of what? Negative, right? Just like it would be on a graph, right? Where above the x-axis is positive, below the x-axis is negative, right? Same way here. The important thing to note, though, is that at that 0 mark, right, at the 0 mark on the y-axis is called a node. And that's where we are sure that there are no electrons present, okay? And it's called a node, okay? That's called a node. So let's take a close look here, right? Actually, let's go back one slide just so I can show you something real quick. So here, where would the node be? The node would be right there, right? Those are nodes where we don't think there are any electrons at all. Does that make sense? And then over here where the blue is, that's where the phase is positive. Where the red is, that's where the phase is negative. Okay? Does that make sense? I know it's kind of crazy. Say that again? Correct. It's where we think that there are no electrons present, right? It's where we think that there are no electrons present. I know we're jumping into some quantum mechanics stuff here. It's getting crazy, okay? It's getting a little crazy. But I promise you, if you learn this now, OChem 1 will be so much easier. Okay, so this is the next slide, right? Oh, I always do this. I always say things more than once because I talk too much. So here's a p orbital, right? And here's that node you were talking about, that little intersection point, right? okay? And then here is one phase is negative, the other phase is positive. So it actually doesn't matter what the color is. I think they just put the color there to say they're different phases. It doesn't matter what color it is. As long as they're different phases, one is positive, one is negative. It depends on the person who drew the drawing. And like I said, I took some of these pictures out of an organic textbook. So they might have drawn the colors separately from the way they are in your Gen Chem textbook.
And the reason why it's negative on the bottom is because it's underneath.
Yes, it's underneath the node, right? It's underneath the node. Because that's the way a wave works, right? It goes up and down, up and down. And so when you're on the up part, what are you at? You're a positive phase. When you're on the down part, you're a negative phase. When you're up, you're a positive. Down, you're negative, right? I know, it's just crazy, blowing your mind kind of stuff. I know, right? Okay. So yeah, this is a p orbital. P orbitals look like dumbbells. Okay, they look like dumbbells. They're not like excuse me, they're not the balls, the spheres that s orbitals are. All right. So look at this. This is crazy. This is absolute crazy right here, right? Because we're relating these orbitals back to the periodic table. Okay. Check this out. This is the 1s orbital right here, right? This is the 1s orbital. So what could possibly be this atom right here? Yes, exactly. It's either hydrogen or helium. Because they're the only two that only have what? 1s orbitals, right? Because they're up there on the 1s line, right? You see how these orbitals connect to the periodic table, right? I wish you could just draw these up there too so you know which one's which, right? Now we're at the 2s orbitals, right? These are the 2s orbitals right here, okay? So that's everything over here, right? Lithium or beryllium, right? Crazy. Absolutely crazy. Absolutely crazy. All right. And then the last thing that we need to talk about with, as far as, because we're not going to go into d orbitals, they're just too crazy for right now. The p orbitals, right? Notice how it says 2py, 2px, 2pz. The reason why that is because there aren't any 1p, right? There aren't any 1py's, 1px, or 1pz's, right? The first p orbital starts where? On the second row. Does that make sense? Literally, everything that we have, that we've described, as far as atomic orbitals go, all the shapes, all the math, came from the periodic table. This guy in the 1900s, right, didn't know anything about computers, chemicals. All he did was weigh some elements and notice that they had certain weights. Some were more heavier than others. Some were twice as heavier than others, 3 times as heavier than others. And he was able to put together a periodic table that makes sense still today. It's absolutely insane. And this guy was in the 1900s. No computers. Yeah. His name is Mendeleev, by the way. Go ahead. His name was Mendeleev. Well, go ahead.
What?
His name was Mendeleev.
Oh, sorry.
Yeah, no problem.
I'm not here. What did you say for the 2py, 2px, 2pz?
Yeah.
They're the same. They're equal.
They're equal energy, see? They're all equal energy, right? Okay. So the technical term of that is that they're degenerate orbitals. Degenerate means equal energy.
Okay, so since we figured out what elements there could be on the 1s, 2s, how would we figure out what elements there could be?
You wouldn't be able to because there's so many p orbital elements. Okay. Right?
Yeah.
Unless you had the electrons. Unless you counted the electrons inside the orbitals. Okay. Yeah. It will later, not now. It will later. Okay? But really, the reason why it's like that is because that's just a three-dimensional graph, right? You have the x-axis, the y-axis, and the z-axis. Then you have the negative forms of each one, and you just can't occupy, a y and an x at the same time. It has to be all y at the same time, all x at the same time, or all z at the same time. Otherwise, they conflict with each other.
So it would just depend on how many p's it has, is what you're saying. So we go from
That's true. That is absolutely true because you could fill just the 2py's and 2px, but if you didn't have any more electrons after that, then you wouldn't even be filling the 2pz's. That's exactly right.
But also leading with that, so what I'm saying is, so first, when it will matter, we go vertical and then we go sideways and then we go sideways again. Yeah,
that's the order you would go. You go y, x, z. You think it would be X, Y, Z, but like chemists are weird. So, and honestly, you could do it that way, but it won't matter.
Why is that out of order?
That's just the way they drew it, actually. Because whenever I write it, I always write it P X P Y P Z. So really the order doesn't matter as long as they're not like occupying the same orbital. As long as you don't have more than two electrons occupying the same orbital. Okay? And that's actually the next slide right here. Okay? So now, since you've learned so much about electron configuration from our last assignment, right? Let's put electron configurations into molecular orbitals, right? So let's look at, for example, let's do nitrogen, okay? Look at nitrogen. This is its electron configuration, right? 1s, how many electrons? 2. 2s, 2, right? And then 3p, so that 2, what is it? Sorry. 2p, I'm looking at the wrong one. That's what happened. 2p3, right? So literally, you can take your electron configuration, draw out the orbitals, right? Draw out the orbitals and fill them up so that you can see where the electrons are, right? So these are all lone pairs right here, right? There's lone pair, and these are all what? Bonding electrons, because they're not paired with anything yet, right? Does that make sense? So to answer your question, it doesn't matter. See, 2p, it doesn't matter whether it's X, Y, or Z, right? Sure.
So since you said we have to call all of the X, and the Y's, and the Z, so the two bonding ones, they go like up and down, so it has to be X, and then the other one would be like a Y.
So that's the interesting thing about it, right? So there are these 3 rules, right? I'm going to answer your question with these 3 rules right here. So off-balance principle, Pauli exclusion principle, and Hund's rule, right? The question that you're asking about is actually Hund's rule. Hund's rule actually says that you can only fill up electron 1/2 at a time. So you would actually you wouldn't go like 2p and add another electron there first and then go to the next one, right? You'd actually have to go 1, 1, 1 until you start over again like you do on oxygen and go 1 on the first one again. So,
Yeah.
go ahead.
For each orbital, you would obviously put the orbitals out and stuff, and then you fill them going 1, 1, 1, and then the next line would be 1, and then the next line would be 1.
Right.
So you would put
So, but you have to do one orbital at a time, right? So count up the number of electrons first, right? And then, for example, I'll actually write it for you so that I don't, So let's do something super easy, right? Notice here we have hydrogen, right? That's what hydrogen's electron configuration, 1s1, and there's 1 electron there pointed upwards, right? But then when you get to helium, right? You get to helium, and now there's 2 electrons there, 1 pointed upwards, 1 pointed downwards, right? But then you get to lithium. What you have to do is actually fill up the 1s first, then you get to the 2s, and then you put that last one there, right? So you have to start at one energy level at a time. So once you get to the p orbitals, they're all at the same energy level. That's when you start filling them 1 orbital at a time, and then you have more than 3, you start over again, right? Does that make sense?
So you start over on the same line. So
Yeah.
whenever you put
Yeah.
other triangle. Okay.
Yeah. This is energy right here, right? And then these are all the same energy right here, right? So you start at the same energy first, right? So for boron, for example, you would have put down 2 electrons for boron first. Then you put down 2 more electrons for boron there. Then you go up there, right? So for carbon, you put down 2 electrons for 2 electrons for carbon's 1s orbital, right? Then you do 2 electrons for 2s orbital. Then carbon still has 1 more electron, right? So there's 2 more electrons left, right? You have to fill up that first, 1/2 first, and then fill up that 1/2 next, right? And then if you had more electrons, you keep on going until you start over again, right? So 1/2 at a time, all on the same energy level first. Does that make sense? Does that answer your question?
Yes, that makes sense, but I think I'm confusing the part before. I think I'm doing too much in my head.
Yeah.
So I'm going to explain to you what's in my head, and then
Yeah, no problem.
So in my head right now, I'm connecting X, Y, and Z to those three spaces,
Yes.
and so you said we have to fill up X first, but
Not fill up, but put one in X first.
yeah. Okay, so not fill up, just put one in X
Yes.
first. So
And then put
in
one
the
in
picture,
one.
we would do like, if they had three, we would do one X, one Y, and one Z.
Yes, and then when you have more, one, yes, that's exactly right. That's exactly right.
Because before I was getting like, do your X's and then do your Y's, and then do Z's, so you're saying do one X, one Y, one Z, and then go back to more.
Exactly. So all of that stuff you're asking is these rules right here. So the first rule is called the ask-out principle, and that one says you must fill the lowest energy first, right? And then the Pauli exclusion principle says you cannot have two electrons going the same direction. So that's why there's one going upwards and one going downwards, right? And then the Hund's rule says you can only fill up orbitals one half at a time. So those are the three rules that we just answered just by talking about just now. Does that make sense? Right? Cool. Any problems? Anybody lost or anything like that? Yeah. Go ahead, Mary. What's up?
We're not looking at the number of
Almost hurt my leg.
on the periodic table.
You are. It corresponds to where oxygen is at the periodic table.
That's the same thing as like the
Yes, it is. It is literally the electron configuration. Huh? Yes. They're literally the electron configurations, right? But you're using the electron configurations just to fill up the orbitals, and they're the same names. Huh? Yes, literally, like tallying it off. That's exactly right. You look at oxygen's electron configuration, that's the same thing as oxygen's electron configuration right there. Right? Because it's 2p what? 4. 2p4. Right? Fluorine is what? 2p what? 5. Exactly. 2p5. This right here, these orbitals directly represent what is on the periodic table. Right? Does that make sense? All right. We're going to answer one question before we end class today, and then we have lab. Here you go. Not long at all. I think like 30 minutes. 30 minutes, maybe 40 minutes. What's up?
Do we need to be in proper lab attire?
No, we're actually doing lab in here today. Yeah. All right, answer your last question. Scan it and answer your last question, and then you can take a break before lab. And if you have more questions about today's lecture, since it's so short, I guess I can make myself available to you to answer questions about today's lecture. I think so. I'm pretty sure. There's not much to go over today. To be done with lab, yeah. Yeah, I don't think we're going to be in lab long. I do. Yes. Do you want me to teach your discussion? Why? Oh, thank you. I just talk loud is what it is. I talk really loud. They were telling me to close the door the other day. You should meet me when you're breaking the rules in lab. Then I really flip out. So, for one of my labs on Monday, they were going in there without any like closed-toed shoes, and I flipped out of them, told them to go home and get some shoes, or they're not going to come lab. Well, because you don't want people dropping glass. Yeah. Really? Yeah. Yeah, it does. Well, but that's a serious thing though, because there's glassware in there. I don't want people cutting up their feet, right? So you need to wear closed-toed shoes in the lab. Cover everything from your even socks to cover your ankles too. Because what if something spills on the ground, right? Then you're going to get acid between your shoe and your pants, and I'm not going to be the one to take care of you. So, all right, has everybody answered this question? No? Sorry, we're talking too much. I apologize. Oh, let's switch over. Oh, sorry. Sorry, you hadn't scanned it yet? Sorry. I was going over to the answers. I mean, to everybody's responses. Right, one more response. We're waiting for one more response. Oshana, did you scan it yet? Just a minute? Okay. Oh, okay. All right. Okay. All right. Well, at least most of you got it right. Okay. Which principle states that no two electrons can have the same spin? I can give you a little bit of leeway here because I told you not the same direction, right? But the technical term is not the same spin because electrons either spin up or they spin down, right? And so the Pauli exclusion principle, which is B, says that no two electrons in the same orbital can have the same spin, right? So good job with that one there. All right. There will be an assignment that will be posted, but it won't be due until midnight on Wednesday of next week, okay? Because we have Labor Day. So take a break. Come back here for lab at 1:30. Yes, here. What happened? Isn't discussion on Monday? I'm like, isn't today Wednesday? Just making sure. No, you can't. You can, absolutely. I'll lock the door. But we're not going to the lab today. We're staying in here today. Yes. That's why I said go. No, not at all. That's why I said go take a break, come back at 1:30, meet here. Yes. I thought you were master of Star Wars there, and I was like, no, that's not right. What's up? Crazy, right? It smells like good. I like the smell of chemicals. Yeah.
So I looked, and I know you said that the handout that you posted was not required. And then I know that you just said that we needed to have the handout either on our laptop or hard copy.
I'm literally just talking about it. We're not turning anything in.
Okay, so there was no pre-lab.
No. All right, everybody, go take a break. Everybody go take a break. Come back at 1:30 for lab. 1:30 for lab. We're doing it in here. We're doing lab in here. You don't have any more jokes for me? What really makes me mad about the last one you said is that I told that joke to my girlfriend and she got it immediately. And I'm like, dang it! What the heck? I should have seen that. That's a good one though. That was a good one. Thank you for that. Yeah. All right. Anybody have any questions about today's lecture while we're in break? Don't forget to turn in your assignments at the end of the day, too. You'll probably all get 2 points if you didn't get those right. The two electron configuration ones, if you got them wrong, you'll get the points back. Because for some reason, it was like the wrong answers in there. Craziness. How are you feeling, Mary?
No, I don't know what the boil on this lecture. I'm not gonna lie. I'm just gonna have to go through it again. My brain's not.
Iodine negative is the KR 42.5S25P6.
Yes, that's correct.
Did you have to do a space or?
No spaces.
Does that matter?
It matters in there. It doesn't matter when you're writing it to me, but I think you're one of the ones that got it right.
Because I did two different. The first time it said it was wrong. When I did it, it said KR was. So then I wrote the whole thing down, and it still said it was wrong.
Well, remember, because I said at the beginning, for some reason they had that right answer incorrect in there. So I corrected it. So try it again, see if it gives you the right answer now. Because both should fit in there now. No spaces. Yeah, no spaces. Try it again with no spaces. What about it? What about this is hard for you right now?
It's just a lot of information.
Yeah, I know.
I don't know. My brain's just off today. I normally get it, but I just don't get it today.
Don't worry. I mean, I think that we are still all trying to get used to being face-to-face again, number one. I'm glad that we have a little holiday in the middle of the beginning, because I need that.
Yeah.
Because I'm so behind. You what?
Yeah, I don't think I need touching something.
Are you staying awake in here at least?
Yeah.
That's why I talk so loud. My old boss used to say, you want them to be awake and remember, say it loud and dirty. I can't say the dirty part because I get in trouble, but I say it loud.
I don't know how I got most of my classes A's. I thought it was,
Hmm.
and then I would wake up like 2 minutes before class would end.
Yeah.
Yeah, me too.
Okay. So do you have any questions specifically right now? We can always talk about it later too.
I probably will in the next couple of seconds.
Okay.
I just haven't read the question.
Okay. Call me over if you need anything. How are you feeling about all this stuff?
It's okay. It's a lot of reviews for the Kim one that I took back to 2018.
Well, it's a good thing we're doing it again.
Yeah.
So,
Kind of refresher, but I still do actually have my.
your notes from them? Or your book from them? Oh, your notes. Oh, I'll get that for you. Oh, your flashcards. Look at that. I mean, I'm not going to make you make flashcards.
These, like, you know.
Oh, because they make you memorize that stuff.
Yeah.
I'm not going to make you memorize. I'm not going to make you memorize any of that stuff.
No, it's okay. It's good. Like, this stuff, it kind of there, but yeah, it'll be good. I feel like their homework assignments help.
Yeah.
So then I can see where I'm at.
Yeah.
Yeah, these are
Are they congruent with what we're talking about?
some of this is like super basic, so it doesn't matter.
Yeah.
It doesn't go in here, but towards the end, like all this.
Oh yeah. That's right. I told you about that. Yeah.
So we were
Yeah.
really in depth, but
Yeah.
it took a while to like
Who taught you that one?
I was at a junior college, Dr. Arrington.
What school is that?
Nursing college out in Irving, Dallas. It's a Dallas community.
Oh, okay.
Yeah.
Okay.
I wasn't in Karen County now.
Got you.
I did go really in depth.
Good.
Like 3 years ago.
It's okay. That's why we're spending so much time on it now. Because you're not going to get anything later if you don't get the stuff now, right? Whew. You'll understand it again. You'll understand it again. Yeah. So how's Southern doing with all this?
It's good.
I know it's getting a little complicated.
Yeah, so that's why I go back and watch the YouTube videos and then take notes then.
Yeah, it's a good idea. Absolutely. Because for now you can listen, and as soon as a question comes up, you can ask me. But then all the real material is going to be in the YouTube videos. So I'm glad you're doing that.
Yeah, I was just about to say, and I just like how open you are, because some teachers like seem closed off that make us scared to ask questions, but with you, we know that we can talk aloud. And
Oh yeah, absolutely. I mean, how else are you going to learn this stuff, right?
No, I completely agree.
How are you feeling, Stephanie? Just okay. What's bothering you about the new stuff? Well, the stuff we talked about today, anyway.
Nothing here is bothering me. Calculus is bothering me.
Oh, calculus bothers me too.
I'm like not getting it at all.
I can barely do a derivative myself. Yeah. And I had, oh my God, I got all the way up to like differential equations before I had to stop. And I can't do a differential now if I had to, you had to.
Pre-calculus, and I'm like, how am I going to make it to regular?
I'll tell you what though, pre-cal is actually harder than regular calculus. Yeah.
I took it in high school, and I still remember concepts of high school that I can listen to. And he's like, reading straight from the book.
All right, how are my Hufflepuffs doing?
They're doing.
It's just you two now. And if I join you, because I'm a Hufflepuff too.
I was gonna mention that earlier. I was like, you should be on our team.
Yeah.
But I was like, that'll be cheating. You've got to know all the answers.
Only because I wrote them.
Yeah.
Not because I know them. So, no, I'm kidding.
I mean, you have a PhD,
Yeah.
so I hope that you kind of know it.
I'm just, secretly, I'm winning this told you in a minute.
Well, you're
Yeah.
doing a good job.
Thank you. Appreciate that. How are you feeling, too?
Yeah, pretty good.
You're feeling really good? Not really good or very good? Yeah, yeah, yeah. Are you watching my videos? Is that helping? Like having to be able to go over that again and again, watching it over and over again in the videos? Mhm. Say again? Oh, other videos. They're not as good as mine. I'm kidding. I'm kidding. No, totally.
But I like that you post them because I don't know if you noticed that I don't usually take physical notes.
No, I'm fine with that.
Well, I have like a method that I use that works really well.
Yeah.
Where like I'll read introductory material before,
Yeah.
and then I'll listen to you because I feel like whenever you're in here explaining it to me, it's like a different like aha moment.
Yeah.
You know? And I can't like write and listen at the same time.
No, I totally
And
understand.
then later, whenever I feel like I have a good understanding of the material, I'll watch the video and then I'll pause it and then I'll write my own notes.
Yeah, yeah, yeah. And that's why I put up the video, so you can take notes at your own pace,
Yeah.
right? I tried to make the first one work, but that didn't work out. But this one should work. So, and the one before that worked too. So, but yeah, I'm glad. But I know that, was today's stuff okay, or was it a little bit complicated?
Today's stuff is a little complicated.
Yeah. All orbitals are complicated.
Yeah.
But just remember that the periodic table tells you what the orbitals are.
But like I was saying last class, like I remember learning about this stuff in chemistry 1, and I remember going, oh, okay. But like the way that you're explaining it is like, oh, okay, like that is what they were talking about.
Yes.
So I guess learning it twice.
I took organic chemistry 3 times. Don't even feel bad about it. And now I'm a doctor. So don't even worry about it, okay? Don't even worry about it. So I failed my very first general chemistry test. I got a 0. I think I told you guys that. Did I tell you that? I did? Oh my God. My very first ever general chemistry test, I got a 0.
Wow.
Yeah, an actual 0 because my professor had this like weird system where he graded on a scale of 0 to 5. So if you had anything that was like D or F work, you wouldn't get the points up to like 69. So everything below 69 or everything below 60 was a 0. So I.
Your grade, like if everybody got an A, everybody didn't get a grade.
Yeah.
Everybody didn't get an A. They didn't grade based off of your grade. They based off of your grade. So
Yeah, it was very similar to that. Yes.
And it was whenever I was on the pre-med track
Yeah.
and UTD.
Yeah.
And I was like, this is so because I had got all the answers right.
Yeah.
One of my public health professors, whatever.
Yeah.
And I got all the answers right.
Yeah.
But somehow she had gave me this low grade, and I was like, I don't understand it. She was like, well, it just didn't do as well compared to. She did it in groups of 5, so she would take random.
That's weird.
5 random students. She would bring from 1 to 5.
That's really
and then
weird.
that would be your grade. She would take another random stack of 5 students.
What if your random group had a whole bunch of people in there that did really, really good, and another group did really, really bad?
Yeah.
But then at the end, you report all the grades together.
Yeah, I mean, I did really well in the class.
That's crazy though. That's so crazy.
I did everything correctly in the class, but I got to be in it.
Shut up.
So many of us went and complained.
That's the craziest thing I've ever heard in my life.
There's something that we should do. She's one of those teachers that.
That's just crazy. That's just crazy. Okay, let's get started on lab real quick here. Did she really? God. That is crazy. That is so crazy. That will not happen in here. That will not happen in here. All right, I'm going to stop the recording unless you want me to record talking about lab.